And get your name tags out because I still don't remember your names. It's unlikely that I'll remember all your names by the end of the semester, but I'll keep trying. So David, there's nothing showing up on those screens. Why not? Right, folks? Thank you, Akansha. Since I don't know your name, it's very important, that name tag. Yes. You actually got a name tag. That's beautiful. Right? Oh. Okay. Hey, Puro, where's your name tag? All right, guys. Magic. Okay. So first, before I begin, this is my, we're going to be talking about yet another form of decomposition today, non-negative matrix factorization. Many of the slides and almost all of the examples on these slides are actually due to my good friend Paris Maragdis, who may now be at MIT. I don't know. He's a professor in UIUC. So, but this is from when we did when we worked together. So here's a quick recap, right? This was the problem that we actually looked at when we were performing eigen decomposition or the Karhanen-Love transform when we were trying to find bases for data. So we found eigenfaces. What were these eigenfaces? The eigenfaces were bases. We have some data matrix. In that example, our data matrix was a matrix of faces. And then we tried to find a set of bases B such that every vector over here could be expressed in terms of these bases. Now, you could just use your standard orthonormal bases and it would work just fine. But then we wanted to come up with a different set of bases. And in those cases, we were looking at eigenfaces as our bases. Now, what could the purpose be to actually want bases of this kind? So for this, again, the problem of finding these bases, there were two problems here. Of course, the first was finding the bases. In the case of faces, it would be finding our typical faces or eigenfaces. If you're working with music, then these could be, trying to find the note-like structures that compose the music. And then once you found the bases, the next problem was actually figuring out how those bases combined to generate each data point. Like in the case of the faces, how did you mix your eigenfaces to generate any given data instance? And then going back to our problem, why do we want those bases? Why do we even bother with doing this? Now, if you'll remember, I mentioned even when we were talking about linear algebra that the biggest problem in machine learning, or one of the biggest problems, is finding the appropriate representation for a data. So finding the bases that best capture the space, the manifold that the data live in. And what would the benefit of this be? Most importantly, this is going to give you a better representation. If your bases are properly defined, then your representation is going to have some kind of semantic to it. For example, if notes are my bases, then I can just write a score. A human being could read the score and they know what the music is. In the case of other kinds of compositions, if my bases were parts of faces, I could just describe a face and you could kind of visualize what the face looked like. So having the right set of bases gives you a semantic characterization for the data. And having semantic characterization makes this much better suited for statistics, some kinds of statistical methods. So this was one reason for wanting a different set of bases. The other reason was dimensionality reduction, where we saw, for example, that if you got your bases just right, the first few bases captured most of the information or most of the energy in the data. And so even if you didn't try, if I had 1,000-dimensional data, then in the naive representation, I'd have to give you 1,000 numbers to characterize the data fully. But if I use the appropriate bases, I could maybe get away with just 50 numbers, because whatever is there in the remaining subspaces is not really very much. I'm losing some information, some energy, but then we want to find our bases such that the amount of information lost, the amount of energy lost is least. And if we do that, then I could just use a lower dimensional characterization of my data. So in our eigenfaces example, if I just got, or in the music example that we saw in the linear algebra class, for that particular section of music, just 5 unique combinations of notes recreated the entire music. So I didn't need to give you a 1,000-dimensional vector for each vector. I could have just given you 5 numbers, and you'd have gotten the music right back just fine, right? And there's also the third aspect we mentioned when we were talking about bases is denoising. That if you find the appropriately organized set of bases, then the early bases capture all the most important information. And then maybe the later bases, which carry the least amount of energy, mostly carry information about noise, like in the image of the corrugated sheet that I showed you. The fluctuations of the sheet could be viewed as noise. So these are the 3 reasons we want to compute good bases. And we saw one method of doing this, finding eigenvectors of the correlation matrix. This was the Karanin-Love transform, or PPCA, which finds the eigenvectors of the covariance matrix. And in these, satisfy most of our requirements. I gave you 3 requirements to satisfy most of them. What do I mean by most? What am I missing? Can anybody guess? What would I be? Do the eigenbases have an energy compaction property? Do they represent most of the information and the least number of numbers? Yes or no?
Sometimes they're not really good for semantic capturing.
They're not good for semantics. Eigenbases capture most of the information in the smallest number of bases, right? Smallest number of numbers. Also, if I were using eigenbases, then you can sort of imagine that the trailing end of the bases capture noise, but then they lose semantics. What do I mean by losing semantics? Let's go back and look at this example. Look at images 2 and 3, right? So one of the characterizations of eigenbases is that they are orthogonal to one another. And here is a rule that if I have a set of orthogonal vectors in any number of dimensions, then no more than one of these vectors can be unipolar. What I mean by unipolar, or where all the components have the same sign. So if I can have one vector which is all positive or all negative, and every other vector must, by math, have some positive and some negative components. There's no other way they can all be orthogonal otherwise, because components must cancel each other. This is math. And so you end up with the second and third bases over here, the second and third eigenfaces. They have negative components, but these are composing images. What does a negative pixel imply? If I'm looking for semantics, what is a negative image? Or this is perhaps more poignantly brought across when we think about sounds. If I'm looking at a spectrum with energy, then, if I'm trying to learn notes from music, what's a negative note? It doesn't make any sense, right? So the thing with orthogonal and with eigenbases is that they have the energy compaction property, but they're lacking this essential aspect of semantics, right? So there's a poll. Okay, I'm staring at you, right? Option 2. So which of these 3 is the most correct? Just option 2, right? The representing a face in terms of the weights of our eigenfaces only has the ability to reduce dimensionality, but loses essential components in it with, but leaves the essential components in it with the least loss of energy. The rest of the 2 properties don't necessarily hold. And so orthogonality and energy maximizations are statistically meaningful operations, but may not be physically meaningful. And so today we're going to look at a physically meaningful constraint because we want semantics. And one physically meaningful constraint is non-negativity. So I like to start with this little parable. How do you go about it? Once upon a time in a faraway land, there was a rich king who discovered a previously unknown recording of a beautiful piece of music in his attic. Unfortunately, it was damaged. And he wanted to listen to it. He wanted to find out what it really sounded like. So he hired an engineer and a musician to solve the problem. And the engineer, of course, went off and wrote grant proposals and applied to the NSF, got millions of dollars. And after published many papers, and after several years, he came back with a complete but rather scratchy piece of music. The musician, on the other hand, just listened to this engineer's music, whatever scratchy piece it was, and transcribed it. And then he went off to his trusty keyboard and played out the music. Who do you think produced the better music at the end of the day? The musician. He got the princess, right? So this is what we want to do. So this is, now I'm cheating here when I tell you that the musician spent 10 minutes on the job and the engineer spent years. Because to spend those 10 minutes doing this job, the musician has spent years and years of his life being trained. Now, what has he been trained in? In discovering, listening to the music and identifying what the essential building blocks of music were so that he could go back and put them together and play the music. So, let's ask ourselves again, what composes an audio signal? What composes, for example, music? Here, there is no sound. Hello? Okay, so here are a bunch of notes. Here are a bunch of chords from the same notes, right? And here, more complex piece of music. But guess what? This last bit was composed of the same elements that you just heard earlier, and a few extra notes. So what composed this more complex music? It was the notes, right? So our problem here then is to think of how did those notes compose the music? Semantically speaking, if I asked you what composes music, you're going to say notes. Maybe you're going to say chords. But why notes? Why chords? And there was a very semantic aspect to it. The composition was constructive, meaning if I played 2 notes together, one note does not suppress the other note. You hear both the notes. And it's linear. If I play 2 notes together, if I play an A and a C together, the C doesn't distort the A to an E. You're going to hear the 2 notes, right? So it's a linear composition. And this is what is giving us the semantic compositionality of the model. So our problem is to try somehow to analyze the music and determine the compositional building blocks of the music, to come up with the notes from the music, right? And how can we do this? From the music alone. So for this, first, we need an appropriate representation. For audio, I'm going to use power spectra. And the nice thing about power spectra is power adds. If I add two random signals, uncorrelated signals, the power in the sum of the two signals is the sum of the power in the two individual signals. And so when I begin representing signals, audio in terms of power spectra, if I add two signals, just sum them up sample by sample, the power spectrogram of the sum is going to be approximately equal to the sum of the power spectra of the individual segments that were added. So we're going to use a power spectral representation. And this has this nice property that this is compositional. If I add two signals, you're going to hear both signals, the power and the resulting signal as the sum of the powers. And it's also linear. If I add two signals, one signal is not going to distort the other. It's an additive composition, right? So once I come up with this representation, then I can think of how I might imagine a piece of music was constructed. So I could have, for example, a bunch of notes. And it's going to be the same bunch of notes, but then, so in our case, rather than notes, they're going to be power spectral structures, spectra. And the characteristic of power is that it's non-negative, right? The entire thing. Now, if power were negative, if it had negative components, I could add two things and they could begin canceling each other out. But we saw that that's not the case, right? We want things to be strictly compositional. And so power has this characteristic. And now, if I'm playing notes, in the first section of the music, I'd be using these notes and striking each of them with some energy. And that would build the first segment of my music. Then I take a step ahead. I'm going to use the same bunch of notes, but I strike them with a different amount of energy. And so it's going to compose the second segment of my music. And so in each little section of my music, why is this? I think I've run out of battery. So in each little section of my music, I'm going to keep adding these things with different weights. It's the same bunch of notes, they're just being played with different energies, right? And so each frame of sound is composed by activating the same set of spectral building blocks, but each building block is being activated by a different amount. So each individual frame is composed by combining these building blocks at different energy levels. If you want to think of this in terms of notes, it's like saying that you're playing you're composing each segment of music by strumming the same four notes with different energies, right? So our problem now is, given only the final composition, we want to work our way backwards and find out what the notes were. So from only listening to the music, we want to learn all about the musical notes. What we are trying to do is to go back and algorithmically try to be the musician. The musician spent a lifetime listening to individual notes and music to find out what the building blocks of music were. We're going to try to short circuit the process, provide a bunch of examples, and let the algorithm learn to be the musician. So in math, if I have my bunch of notes, then each of those notes can be thought of as a basis vector. And so each vector in my spectrogram is a different weighted sum of the bases. But the thing is that the bases are all non-negative. They are power. The weights are also non-negative. You don't negatively play a note. You only positively play a note. And the resulting composition V, that's a power spectrum also. So that's also going to be non-negative, right? And so each frame is a non-negative power spectral vector. Each note is a non-negative power spectral vector. And so each frame is a non-negative composition of the notes. And this is what non-negative matrix factorization is all about. We want to figure out from listening to these guys, which is the final set of vectors V, what the bases that compose them were. But then we're going to impose realistic physically motivated constraints, in that we know that when it comes to sounds, the building blocks are all non-negative and the composition is also non-negative, right? So Maya, just shut your laptop, will it? Yeah, thank you. So and because everything is non-negative, this is non-negative matrix factorization. So NMF is a compositional model. And all of my data are assumed to be non-negative. I'm using music as an example, but images are no different. You never see a negative pixel, do you? So when I have collections of images, every image is a collection of non-negative pixels. And so I can apply the same techniques to these. And we assume that there's a bunch of non-negative bases because a note must be a non-negative thing, right? A face must be a non-negative thing. So we have a bunch of non-negative bases. And these are combined in non-negative ways to compose my data. We're using compositionality as our criterion. And so every vector V is going to be some weighted sum of my bunch of bases, where the V, the B, and the W's are all non-negative. They could be 0, but they're not negative, right? No subtraction is allowed. Any questions? Simple enough, right? So what does non-negative composition mean geometrically? Now, firstly, if I were to draw non-negative vectors, all non-negative vectors are going to be only in this positive orthent. Because if they were in any of the other orthents, they're going to have
Negative bus.
they will have negative components, right? Number one. Number two, if I'm only allowing these things to be scaled by positive amounts, where will the compositions lie? So this is B1, this is B2. If I look at things like W1, B1 plus W2, B2, and I require that W1 and W2 are also non-negative, then where in the space will these compositions live? Anybody? Between the two, right? They can only live here. Because if I did this, then when it's purely B1, it's going to lie along this guy. When it's purely B2, it's going to lie along this guy. If it's some weighted value of B1, it's going to be something of this kind, plus some weighted value of B2, where the weight is positive, it's going to be something of this kind. It will lie strictly inside. The moment you have something outside, the only way to get there is to go up this way and come back this way, which means you're multiplying the bases by a negative value, right? So non-negative combinations basically say that all the data lie within a cone, where the cone are composed by the bases, the outermost of the bases. Make sense? Right. And so if a vector lies outside, the only way to compose that vector using these non-negative bases is to flip the sum of one of these bases. And so when I'm speaking of non-negative matrix factorization, what am I really speaking of? I have a bunch of data shown, for example, by those red arrows. They're all non-negative. They all live in the positive orthant. And I want to find a bunch of bases, basically those blue arrows, such that every single one of my red vectors can be expressed as a non-negative combination of these bases. So if I had these two bases, for example, this vector can be composed by these two bases in this manner, right? This vector is composed by the same two bases, but scaled in a different manner. Here's a third one, composed by the same two bases, but scaled in yet another manner, right? So we have three different ways of composing these. So can you shut your lap phone, please? Thank you. Right, so writing this in a, yeah.
So when you say that I can like between the B1 and B2 bases, what if the first base is 0 and like so it can lie outside that two bases if it is W2 plus the B2, right?
No, it cannot, right? If the B1 is 0, it's going to be on this line.
Yeah, so anything plus B2 would be outside that thing.
No, it's because anything plus B2, what is this anything? These are the only ones that are allowed. Correct? So there's nothing that you can compose that's outside that count. Okay? Now, if I were to want to write this whole thing in algebraic form, I can put all of my data vectors as a matrix V, right? All of my bases as a matrix V, and all of my weights as a matrix W. So I'm going to have these would be my vectors V. These are going to be my bases. And then here, this set of weights represents how these are combined to compose this guy, right? This set of weights represents how these are combined to compose this guy, and so on. Correct? And so I can write the whole thing as V equals B times W. And each column of B has a scaling factor that composes the corresponding column of V, one corresponding column of V, right? So again, this is what it is. When I'm trying to learn the bases are non-negative. They lie in the positive orthant. And so the blue lines represent the bases. Any vector that lies within the bases is going to be a positive combination of these guys. Any vector that lies outside is going to have at least one of these things be flipped. And I am trying to find, given a bunch of data, and so there will be an error, right? The closest non-negative composition I can find is going to be on the boundary of the cone. And so there will be an error. When I try to find the non-negative bases that combine non-negatively to compose all of my data, I'm trying to find the bases such that the total squared error or the total error shown by the dotted red line is minimized, right? So the NMF representation characterizes all data as lying within a compact convex region. Compact meaning it encloses only a small fraction of the entire space. And the more compact the enclosed region, the more it localizes the data within it. So here's the key bit between something that's the difference between, say, non-negative matrix factorization and something like principal component analysis. If I have a bunch of data, like so, then principal component analysis and all of those other characterizations are going to try to characterize the densest region of the scatter. They want to capture as much of the data as possible. Whereas NMF is trying to make sure that all of these can be composed, non-negatively. So it's actually trying to compose the boundary of these data points. So statistically, the two are very different. Your standard techniques try to capture the mode of the data. These non-negative compositions try to capture the hull, the boundaries. So it characterizes distributions through the boundaries. If you want to go outside and message, it's okay. Okay. Yeah. It's the bias. So here's what we want. We want the bases to enclose the data as compactly as possible. But we also want them to enclose as much of the data as possible. Otherwise, you're going to begin misrepresenting some of the data, right? So here's your proof. All right, most of you are done. So Abhishek, is the first statement true? No. Okay, Aisha, what about the second? What about the second one? It's true. And Vidur, what about the third? Also true. And so it's a linear decomposition that can be used to decompose any real matrix. No, the data must be strictly non-negative, right? And it decomposes matrices into a product of matrices. One of these components represents the bases, the other represents the modulations. I didn't ask you to answer the last two, but all data are required to be non-negative. And it represents a semantically meaningful way of deriving bases for data that only combine constructively. I have not shown this last claim. It's a claim that I make, but I'm claiming that by imposing a semantically meaningful constraint. So when I perform something like principal component analysis, the only constraint I impose is that Severity, can you shut your laptop, please? Thank you, right? So the only constraint that I impose is that the energy must be conserved. There has no semantics to it. So now I'm imposing an additional semantic constraint. I know that in the real world, these data are constructively composed. And so I've imposed the extra constraint of constructive composition. And my claim is that by adding this extra constraint, I'm going to get semantically meaningful bases. Okay, so let's see. Again, the problem is, yes. The modulation, remember, the bases and the weights, right? W was the modulation always, yeah. So but remember, I explained this back in the linear algebra class that I had sinusoids and I had their modulations, right? That is the modulation. That makes sense? Okay. So we were given a collection of data vectors like the blue dots. We want to find the set of bases such that they enclose the data most compactly. Now, we don't explicitly impose the constraint of compactness. It just kind of happens. And let's see how. So first, to learn the bases, we want to express every training vector as a non-negative combination of the bases. So every vector V is some weighted sum of the bases, as shown by the equation on the top, right? So in algebraic notation, I can represent all of my training data vectors as a matrix V. So if these are d-dimensional vectors, it's going to be a D cross N matrix. You know, V is going to be of this kind. This is D, this is N, and this is my vector V, right? I can write my bases also as a D cross K matrix. The columns of this matrix are my bases. And consequently, what will the size of my weight matrix be?
A by N.
It's going to be A cross N, right? So all the basis vectors are in matrix B, and so the weight matrix is going to be K cross N. And ideally, V should be exactly equals to B times W. That means I have correctly composed every vector in my training data, right? So now this only holds true if all the training vectors lie within the region enclosed by the bases. But the way we will do it, we're going to use, like as always, an iterative algorithm. The first is you're going to start off with it doesn't have a closed form, because once you impose non-negativity, then these are constraints, and constraint optimization requires Lagrangians and stuff like that, if you will remember, right? You could try to optimize this using this classical Lagrangian methods, or you can come up with more optimal estimators, we will see, such as those we will see. And in every case, you're going to start off with an initial estimate saying maybe the bases point this way, and then keep adjusting the bases until they enclose more and more of the training data and have less and less training error. At some point, you're only going to be leaving out the outliers, and then you're satisfied, right? To do this, first, you need to define a divergence between, is there an eraser here? The actual data and what you can compose, what you're composing using the bases. So I do believe the most satisfying part of teaching is this, right? And seeing all the dust fly off. But anyway, so let's say I have just randomly chosen these two to be my bases. And let's say this is my training data point. Then my best approximation to this guy is going to be this one, right? And now I have an error because I'm trying to compose it non-negatively. And so I'm going to have to define this error. What is this error? Remember, this is the error from the boundary of the cone that I can compose. Or it doesn't have to necessarily be some boundary. It's going to be some boundary surface, not just an edge in higher dimensions. So I don't know which boundary I'm trying to find the error distance from. I need a formula for it, right? So I have to define a divergence between what I'm composing and the vector I want it to be. And the easiest divergence, that one that we're all familiar with, is the squared divergence, the squared norm, right? So this is one, that's your L2 divergence. But it turns out that for non-negative data, there's an even nicer divergence. How many of you are familiar with the Kullback-Leibler divergence, KL? Cross entropy, come on, everybody has heard of cross entropy. You messed with deep neural networks, right? The one thing you're not allowed to mention in this class without failing, right? So you're familiar with deep neural networks? What is cross entropy? No idea? Okay. I'm teaching at least one person. This is nice. Okay. Now, cross entropy and Kullback-Leibler divergence are defined between probability distributions. If I just give you non-negative vectors, they are not probability distributions. So how can I define a cross entropy between two non-negative vectors? I can normalize them, right? And then I can define a standard cross entropy loss. But in the process of normalizing them, I'm losing information about their length. So this is the generalized KL divergence, which is defined between non-negative vectors. This first part looks just a lot like the standard cross entropy. But then the second part is the difference between the sum of the components of the first vector and the sum of the components of the composition, right? And so when the composition is perfect, this error is going to be zero, otherwise it's going to be non-negative. Okay. And this, it turns out, is semantically more meaningful for non-negative data than an L2 divergence. Now let's consider both cases, right? If I'm trying to minimize the L2 divergence, how can I do it? Anybody? If I'm minimizing the L2 divergence between B and BW, how can I do it?
Find a pseudo.
Gradient descent, okay? Or, yes, you're saying?
Oh, I said pseudo inverse, but gradient descent probably works because this is in closed form.
Yeah, Isaiah is way ahead of me, but yes. So here's what I can do. I can initialize my B and W somehow. I'm trying to say V equals BW. And let's say I initialize my B. So then what is my new W if I initialize my B?
B inverse.
Is it going to be B inverse or B pseudo inverse? B pseudo inverse times B, correct? But is it guaranteed that this W will now be non-negative? Okay, so if W is not non-negative, how can I make it non-negative?
Negative elements to zero.
What are we doing in that case?
That's between 0 and L.
So if we went through the optimization lecture, we mentioned a specific technique where we had a constrained feasible set. You remember? A feasible set was the region of the space where the estimate was allowed to lie. And we mentioned a technique that used gradient descent, where anytime your update went outside the feasible set, you did something to it. What did you do? Go ahead. We projected it back into the feasible set, right? So over here, if W hat as a non-negative element, it's going to be somewhere here, correct? What is the projection onto the feasible set?
The boundary.
You're going to be dropping it right on the space. What does that do? What is the boundary? Canyon. Yeah, if it just take anything that has a negative component and set it to 0, and that's actually just a projection onto the non-negative space, right? And so that's what we would do over here. Iterative solution, we want to minimize the E such that B and W are strictly non-negative. So here's what I can do. I can initialize my B, my W, and my B is going to be just B times W pseudo inverse. It's not guaranteed to be non-negative, so I floor all the negative elements to 0. But now I have an updated estimate for B. I can use that B to go back and estimate W, right? And W is going to be B pseudo inverse times. This should have been V, I think, right? Yeah. And that's also not going to guarantee to be non-negative. So I can just floor all the non-negative, the negative terms to 0. I can iterate between these two, and it's a convex optimization problem. I'm guaranteed to get to the optimum in a finite number of steps, right? Does it make sense to everybody? Right. So this is with L2 divergence, very simple. With the KL divergence, things get a little more hairy, right? So here's what it looks like. Now I'm going to try to minimize this error. which is the KL divergence between the composition BW and the original vectors V. It looks a lot like your probabilistic KL divergence, except the second two terms are simply adding the sum of the components of V, the difference between the sum of the components of V and the sum of the components of BW. And when you try to minimize this, you end up with a multiplicative update rule. I'm not going to derive it, but then it ends up looking like this, where I'd initialize my B and W as before, but then every time, this is a component-wise multiply. So I'm going to update my B by multiplying it by this term. And if you actually check out the dimensions of this term, then all multiplications and divisions over there are component-wise. Then this is going to have the same size as B. So, and then once I've gotten my B, I can update my W. And this is again a component-wise multiply of the current W by this second term, which is B transpose V over BW. V over BW is giving you the ratio by which the estimate is off, right? And so B transpose that ratio is essentially how much you want to correct W by at each point. So this guy, since it's a multiplicative term, BW is going to be off by some amount. And so this is going to be off by V over BW. That's the ratio. And so effectively, you're going to be adjusting B by this ratio to reduce the error, but then it's reshaped by the B transpose divided by B. That's just the reshaping, okay? So at each point, you're essentially finding out by what factor is my estimate off. And then you're correcting your parameters by that factor. So how does this work? Again, reiterating, I'm going to have a D cross N matrix V. I'm going to have a D cross K matrix of bases, a K cross N matrix of weights. So each vector in V is going to be composed as a linear sum of weighted sum of my bases. So can someone wake him up, please? You don't have your name tag out, so I can't call you by name. Do you want to go wash your face? Thank you. Or you can come and sit here. I promise you, it's very hard to sleep out here. All right. So, and NMF is learning the optimal set of bases, B, to compose the data. All right. And so let's see how this does it. This was, remember, I saw this was in my first lecture on linear algebra. So this was my Bach's 5 notes from Bach's fugue in G minor. And so this is a spectrogram. It's all non-negative. I have decomposed it into B times W, where B has 4 columns and W has 4 rows. So if I just play out the first column of B times the first row of W, that's going to tell you what the algorithm thought the first note was and how it was played. The second column of B times the second row of W is going to tell you what the algorithm thought the second note was and how it was played. There is no prior information about music that has gone into this algorithm, right? And so here's what you get. These are the 4 notes it has found. And these are the scores that it got all by itself. And if I played out, got the first note, got the second note, it was played twice, third note, 4. It actually gives you back what you expected to get, right? Or here's another example. This is Rita, my wife. She's just saying 5 sounds. Yes, the 5 vowels. And I know there are 5 vowels, but there are actually 6 sounds over here. So let's see what sounds it uncovered. These are the spectra. And here's the first one. So A. It sounds like a ghost. And this Turns out there's an extra sound, there's the background noise. And it got that as well, right? So you're actually pulling out what you would expect to be semantically meaningful units of the sound. And all I did was straightforward algebraic manipulation of a spectrogram. The only thing I did was to impose an additional semantically meaningful constraint. And that gives me this decomposition, right? And so what if I do this with other data? There's nothing magical about nodes. What if I did this with faces? Now, if I asked you to draw a face, how are you going to compose a face? You take a nose, take a pair of eyes, take a mouth. These are the compositional parts of faces, right? Guess what the algorithm discovers? If I just give it a bunch of faces and perform NMF on it, the bases that I get end up being parts of faces, cheekbones, noses, different kinds of eyes, mouths. Beautiful, right? So, yes. So long as the data are non-negative, it's always possible to find a bunch of bases that will compose them exactly. Right? You're just trying to find the tightest set, and that's what gives you this. Okay? So observe that something strange happened here. I didn't actually impose any constraint of compactness. So if I just use my axes as my bases, my axes are perfectly non-negative, right? They would have enclosed everything without any error, but they'd have been completely meaningless. I needed them to come close and make a compact enclosure of the data for the bases to actually begin to make sense. So if the number of bases I ask for ends up being the dimensionality of the space itself, there is high likelihood that the model will simply capture the orthogonal axes and call them my bases. This only has somewhat of a hope of giving you semantically meaningful bases if the number of bases you ask for is fewer than the dimensionality of the space, in which case it's going to pull things together and give you something more compact. Right? Any questions? No. Okay. So NMF essentially becomes a dimensionality reducing representation in this case. And now, suppose I gave you a bunch of bases, and these are non-negative. I gave you a vector, and I said, find me the best approximation for this vector in terms of these bases. Then if we're using just the L2 divergence, then the obvious thing for you to do is to just say weights are going to be what? B plus V. And that's your decomposition. It's going to give you the bases, right? Turns out it doesn't work very well, although it's mathematically perfectly valid. But if you use the KL divergence version of it, then you will end up with an iterative update rule, which is this guy here. And again, here you're only updating the weights. You'd initialize the weights and keep reapplying this formula until it converged, and that's going to give you the optimal set of weights to compose that given data, right? So far, so good. We've learned some semantically meaningful bases. Why? What is the earthly purpose of learning semantically meaningful bases? There's got to be some use for it, right? Or it's not just for aesthetic purposes. It turns out there's a whole lot you can do, which relates to semantics. In my example, I'm going to use speech and audio, music actually, but this applies to all kinds of data. So you can use it for representing data in a semantically meaningful way. You can use it for decomposing data. You can use it for completing data. You can use it for denoising, signal recovery. In the case of music, you can use this for music transcription and so on. Let's see how this works. So I'll give you a simple example of decomposing a signal into its constituent semantically meaningful parts, right? So for example, if I had some music, which was a combination of drums and guitar, how do I separate out the drums and the guitar? Easy. I could take this is like saying, if I know what drums are composed of, if I know the notes of the drums, if I know the notes of the guitar, this is like my musician. I can figure out how the drums were played and how the guitar was played, and then I can separate out the guitar composition and the drum composition. To give you a visual analogy, if I gave you a bunch of green bricks and a bunch of red bricks, and then I gave you a wall composed of both red and green bricks, you could easily enough find out which portion of the wall was composed of green bricks and which portion of it was composed of red bricks, right? Mathematically, this is what it looks like. If I want to separate my music, I'd get a collection of guitar sound recordings, and I can decompose my guitar recordings and find my guitar basses. I'm not going and strumming my guitar and recording each note. This is just being done purely automatically. I could get a bunch of drum recordings and do my decomposition. I get a bunch of drum basses. This is just, again, a bunch of drum basses. And now I know that my mixed recording is composed of both guitar notes and drum notes. So the set of basses that compose my mixed recording is a union of the guitar basses and the drum basses. And so the way they would be combined to compose the music, the guitar basses are going to be combined using the guitar score. The drum basses are going to be combined using the drum score. Since I've got the Bs from my separate guitar and drum examples, now it's just a question of estimating the W. And once I estimate the W, I can just separate out B1, W1, and B2, W2. I've got my guitar and my drums. Again, this 4 lines of MATLAB code. So, and you can do one step further. It turns out that I don't even need to know the second set of bases B2. If I only know B1, I can use the same estimate update rules and estimate B2 and W1 and W2 all together at once, because again, this is just matrix decomposition, right? We know how to do this. So how does that work? Here's a little example. This is Raise My Rent, David Gilmour. And in any of music of this kind, you have this lead in before the actual guitar begins playing or the melody begins, where you have the background playing. So we just use the background here to extract the background basses. And then we extracted both the melody basses and the scores from the mixed portion of the recording, starting from the 10th second on. And here's what you actually get. There's not a lot of math here, right? Or this is the, wait. So it's the background. It's not just music. Here's an example of Norah Jones singing Sunrise.
Sunrise, sunrise, looks like morning, but the clock held 9:50.
So again, you can use the initial portion of the recording to get your background basses, the mixed recording itself to get the melody basses as well, and perform your separation. Again, the math is simple.
Sunrise, sunrise, looks like morning, but the clock held 9:50.
Okay, so you get the idea, right? All right, and you can do more. So for example, if I had a brick wall with holes in it, and I knew what bricks went into composing the wall, I could figure out how to lay the bricks to fill up the hole. The same analogy holds even for filling in data, right? So if I had some destroyed music of this kind, where the spectrogram has got all kinds of regions erased. But if I know what the building blocks of the music are, the notes, then I can figure out how the notes were played, and I can reconstruct the entire music. So let's see how that works. Here's what you would do. You could start off by first learning the building blocks for the music. Just take a bunch of the music, run NMF, get the bases, right? That's like finding the bricks. Then when you get some recording of this kind, for every single vector in the recording, here's what you have. The vector, which is supposed to be like so, has some regions missing. These things. And these regions will be different for each vector. So then I can go to my basis, which also has vectors of this kind, my basis matrix, and erase the corresponding regions of my basis. So basically, I'm learning to ignore, I'm ignoring the portions that are destroyed. And then from this, I can find out how to combine these bases, the weights with which to combine these bases to reconstruct this partial vector. And then I can use this weight with my full basis matrix to reconstruct a full vector. And this I can do to fill in the holes in my data, right? So let's see how that makes sense to you guys. Right, so let's see how this works. So this one was and so we learn what Madonna's bases are from a bunch of real Madonna recordings, which are not destroyed, and use those to fill it in. Again, nothing particularly fancy. All of the math is very trivial, right? Here's one that I like. This was some Latin jazz, but with theories of high frequencies. And you can see almost all of the high frequencies are gone. We're going to try to fill that in, but I don't have the basis for this music. I don't know what notes were played. I don't know what instruments were played. But then my friend Paris is an excellent musician with a degree from the Berklee School of Music. So he went to his keyboard and smashed out this thing. It's his guess that this contains everything that Latin jazz might contain, and he learns his basis from this one. And this is what we reconstruct. The whole thing's back, right? And so, okay, there's a poll, but while you guys are answering the poll, the point was, all I did was to impose some semantically meaningful constraints in my decomposition. And the bases I learned suddenly begin to be semantically meaningful, which means I can do things with them that I couldn't with just any organisms. It was quick. Okay, all right. So Verity, which ones are right? Verity.
I'm not sure thinking about either of those.
Either the first or the second, you raise your hand. Masa, did I see you raise your hand? So which ones are right? So it turns out all are right? NMF can be used for to use the design composition of building blocks. Can be used to determine how the full set of building blocks of all sources can be combined to construct the complete sound, which is what we saw, which means that it can be used to determine the optimal contribution of the building blocks in composing things, which we can now use for separating stuff, cleaning up stuff, reconstructing stuff, right? Very beautiful. Except it comes with a magical unnecessary restriction. And the restriction was, we saw that you cannot learn more than number of bases you can learn cannot exceed the dimensionality of the data. If you do, then you're just going to end up learning the boundaries of the object, which makes no sense. What you really want is for the basis to represent the data as compactly as possible. And it won't happen if you do things naively, right? So also think about real life. If I use 1024 dimensional spectrograms to represent my music, I'm being informed by math that I cannot learn more than 1023 bases. How many notes exist in this world? There are hundreds of instruments. Each instrument can play maybe 8 octaves of notes, right? 8 octaves is 12 8s, 96. throw in hundreds of instruments, each of them has its own different camera, different way of generating music. We can come up with tens of thousands of different notes. The fact that your arithmetic representation only permits 1023 bases has no grounding in reality, right? Nature doesn't care about your math. So similarly, if I have a 1024 pixel image, 1024 pixels can represent millions of different objects, not just 1023 unique building blocks. So we have a problem where, although this kind of works, you're restricted in the number of building blocks you can learn by the math, and we are trying to be semantically correct. So this is kind of violating semantics. So how do you get around that? I can go back into physics. And here's what I have. Although there are 10, maybe 100,000 different notes one can play using all the musical instruments in an orchestra, at any given instant of time, only a small subset of these notes are active. So you can say that I have all of these notes, but on any given column of my spectrogram, only these 3 notes are active. So what is this saying? I can have the basis matrix. Now, if the number of bases exceeds the dimensionality of the space, it's no longer okay to call them bases. The correct term for it is frames. But I'm going to continue calling them bases, although really you should be thinking of them as frames if you want to be notationally correct and correct in the terminology. And so we're going to have all of these very large number of compositional building blocks. But in order to compose any given unit, you're using only a small subset of it. There are 1 million notes in the world, but to compose this particular chord, I'm only generating using 5 of them, right? So if I were to do that, then how does it change the math? My matrix B now is going to contain all of my building blocks, which could be my 10,000 or 100,000 nodes, which means that the vector W is going to have 10,000 components also, as many components as the number of building blocks. But then only a small subset of them are allowed to be non-zero. So you say that however I build it, I want the vector W to have the smallest number of non-zero elements possible. In other words, you want the vector W to be sparse. Okay. So there are 2 things. You can have sparse representations where you want the vector W to be sparse. You can have over-complete representations where you allow the matrix E to have more columns than the number of dimensions of the space. And so you can have sparsity without over-completeness, but you cannot have over-completeness without sparsity. Okay, I have more bases than the dimensionality of the space. Then to get meaningful reconstructions, my W must be forced to be sparse. On the other hand, even with a small number of bases, I can ask the W to be sparse. How does it change the math? So saying that the W must be sparse means that it's the equivalent of saying that the zero norm, which is the sum of the number of non-zero elements in the matrix, must be minimized. So in addition to having the usual divergence, I'll have a second term over here, which is lambda times the zero norm of W. Turns out the zero norm of W is not differentiable. You can't differentiate a column. So instead, you're going to replace this by the 1 norm, which is to say, I'm just going to sum all the values of W, and I want the sum to be as small as possible. And it turns out that minimizing the 1 norm also gives you sparse W's. Now, how does this work? It just turns out that this ends up giving you meaningful decompositions all by itself. Because if I have a bunch of data, consider these 2 bases. If I have these 2 bases, and if I want to generate any data over here, how would I do this? I'd have to scale this, assume the bases are length 1, just for argument's sake. I'd have to scale this up over here by this much, then scale this up over here by this much to get to this guy, right? When are these bases going to be the tightest? They're going to be the tightest when the amount by which I must scale them to compose the data is the smallest. Right, that's when they're going to be so close that they're essentially almost going through the data, and my scaling factor is small. That 1 norm of W is the total scaling factor. And by minimizing it, I end up getting bases which are close in type and also weight vectors which are sparse. That makes sense, everybody? And how does it change the map? It changes to, ignore all the rest of the text. It turns out that in my update rule, all I have to do is to include a lambda in the denominator for my update rule. And that's going to give me sparse weights. In fact, I can also have sparse bases by having a lambda in the bases. Which is to say, for example, in my notes, if I were trying to find bases for music, I can say that my notes only have a small number of frequencies, in which case the bases would also be sparse. So how does this work? So this is about sparsity. What about overcompleteness? Once you introduce sparsity, overcompleteness falls out as a possible property. So now you no longer have any restrictions on B. B can be made up. Okay. So here's what happens. If I don't have sparsity, I'm going to end up learning bases of this kind. But the moment I introduce sparsity, they're going to become passion. So here, just as an example, I have a bunch of data for transfer. And so we're looking at, since it's hard to visualize these things, I drew a plane which went through 0, 1, 1, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0 triangle. And so this is the unit plane. And you can think of every data point as a vector that's going to pierce through this plane because they're all non-negative, right? And so these are the points. And if I just learn, say, 3 bases over here, the 3 bases can be anything. They're not really captured in the structure of the genus. 4, 5. As I increase the number of bases, the bases are no longer have any relationship to the data itself. But the moment I begin imposing sparsity, saying that my weights must be sparse, you can see how the bases sort of quickly compact up. And the hull of the bases actually captures the hull of the distribution of the gradients, right? And in terms of how does this work on real data? I'm not going to play the sound. That's data saying IE, calculation said. And the picture to the left is the reconstruction we got when I didn't impose sparsity constraints. The picture to the right is when I impose the sparsity constraint. And as you can see, it actually identifies the exact location in the recording where each of these sounds is produced. So also for the music. So the one to the left was what I got when this was the Bach's fugue. When I didn't impose sparsity, the one to the right is with sparsity, and you can see how it actually very precisely identifies the exact location with each of these things. So split. Or skip this. This is with images. So here, if I can make my bases sparse or dense, forget about that. But these are the bases, when I try to make the weights, when I just did the standard non-negative matrix factorization to decompose faces, these were the bases I got. And the bases ended up capturing parts of faces, right? But if I try to say that the bases must be sparse, meaning the weights must be sparse, which means that each face must be composed as a combination of the smallest number of bases. Then what bases does it learn? It actually ends up learning face-like structures as bases. It actually learns, this is what I would actually call typical faces, right? It says that pretty much every case in my data is going to can be composed as a combination of a very small number of these guys. And you get all kinds of essential features, like this one's wearing glasses. You get smiling faces, frowning faces that will launch. Very neat, right? And here's another one where we try to, how I filled in the music. I can do the same thing for images. And so in the picture to the left, we took a bunch of faces and we erased a few chunks of the faces. Then we took another bunch of faces and learned bases, and then used those bases to fill in the holes in the faces. And when you just do this using normal training, it turns out that it's really hard to fill in the holes. But as you make the basis set over complete, more bases than that number of dimensions of the space. And then you begin making the weights sparse. Then the signal to noise ratio of the reconstruction basically shoots up, and you can see This is how they're actually reconstructing the faces. You're getting the faces, essentially you're getting it back. There are some errors. For example, I believe this guy was made to smile. No, he's smiling. Instead, he got a gap tooth. Right? Little things like that. But you get the idea, right? I'm able to fill in things in a perfectly plausible way because these are semantically meaningful units. And the reason they're semantically meaningful is that the constraint I applied when I was performing my decomposition was something based on the physics of reality. Right. Speaking of physics, let me take one step further. Here's a poll. I won't go through it, we don't have time for it. But okay, let me pick a random person plane. Is the first statement true? Okay, guys, then what about the second one?
Yeah, yes, true.
True, all right. Yeah, anyone, what about the third? False. And you don't have a name. The name, please.
Johnny.
Johnny, what about the fourth?
Yes.
Yes, that's it there. Right? Sparse representations can be used at any time. You don't need the number of bases to be small or large. Sparsity is independent of over-completeness. They attempt to estimate weights with the fewest non-zero elements. So they effectively model the data as the combination of the smallest number of bases. Now, the solutions will not be similar to non-sparse decompositions because the ones who begin imposing sparsity all kinds of bases. Right? So far, so good. But then let me continue extending the model with more physics. Now here, when I played the sound, these were the 4 chords I played early on. So observe this. It's not merely the sound fading out. Each frequency is fading out at a different rate. So when I played the chord, it was not the spectrum that was the basic structure. It was the spectral patch because the structure changed over time, right? The basic unit is not just one column, it's the entire spectral patch. Whereas the way we did the math so far, I was thinking of my bases as one column, one spectrum, right? How can I extend my math to deal with patches? It's easy, the same thing. I'm now going to assume that my bases are spectral patches. And to compose my music, the first section of the music is composed as sum weighted sum of these bases. Then I take a step forward. And then a different weighted sum of these bases is overlaid on top of that, and everything is added. Then I take another step forward, and yet another weighted combination of these bases is overlaid. And so instead of just doing this one vector at a time, I'm doing this a patch at a time, where the adjacent patches can overlap. Turns out the math is not all that complicated, although it seems kind of hairy when you put on a draw the page. So it's just so I put the math out, here's what it says. This entire spectrogram, but then if I look at any column of the spectrogram, this is going to be the weight of the first basis, right? This is the sum over all the bases of the bases in the current location, that's W0, plus the sum over all the bases of the bases shifted by 1, plus the sum over all the bases of the bases shifted by 2. That's just a crazy mathematical way of writing it. Although it's a convolution, right? Except that I'm convolving pictures. And so when I do the math, since I don't like boring you guys with math, I leave the math for the slides and then I can figure it out, afterwards by torturing you over the weekend. All of these things that come out of this. It works. There's some very, the math is fairly trivial if you actually work it out. How many of you want to see this in a quiz? Yes, we shall see it. The rest of you shall see it and you can personally go to their offices and thank them. And so, and update rules. end up being very similar to what you had earlier. It's a multiplicative update rule. And observe what we're doing here is again, looking at the ratio of the reconstruction to the original. And you're adjusting the original bases and their weights by this ratio. That's about it, right? So how does that work? Here is an example of a recording. This is, again, my friend, this.
One, two.
He's saying the sounds one. He's repeating himself saying one and also saying two. So what are the two basic structures over here?
1 and 2.
The sounds one and two, right? So the patches should be one and two. If I just use the decomposition, let's see what we get. This is the first patch you get. This is the second. And here's the reconstruction.
One. Two.
It's not perfect because, he synchronized himself a little too well. So if you synchronize yourself, it's hard to distinguish between, if the one and two always occur together, then they form the basic unit. So there's a little bit of leakage of one into two, but you can see it actually separates them out, right? Or this is one of my favorite examples. Here I have only one basis. This will, I'm going to go a few minutes over here. The Indians are not being complex. There used to be a play called Adrak Ke Panje, which holds the record for the longest running play in the world. It ran for about 50 years. It was the one actor. Just by one, and entirely by one person. And in 50 years of playing it, they never recorded it in a studio. The only recording we have is on stage. And so this particular recording was from the very last time this was played in my hometown in Texas. And here's what it sounds like.
अरे दबाए देखो आपकी शक्ल देखो ड्रेसिंग देखो वो तो समंदर के नीचे दिख रहे हैं ये जमीन पे कैसे करें छोड़ो जमीन पे आलम होगा किसको मालूम था साहब और फिर उत्तर से आपका घर मेरा घर से आपको रेगिस्तान दिख रहा है
So this is very reverberant. Okay? But what is a reverberant segment? I have my original sound, which is maybe some spectrogram, and this is going to be reflected off one wall, and then you add it on, then it's reflected off another wall and you add it on. Basically, it's the same original patch reflected by different delays and scaled and summed on, right? So this is like having one patch instead of many patches. The patch is repeatedly added to itself with different delays and different scaling patterns. So if I just decompose this using NMF, but using one basis, one patch basis, and then I listen to the patch.
अरे दबाए देखो आपकी शक्ल देखो ड्रेसिंग देखो वो तो समंदर के नीचे दिख रहा है ये जमीन पे कैसे करें छोड़ो जमीन पे आलम होगा किसको साहब और फिर उत्तर से आपका घर मेरा घर से आपको रेगिस्तान दिख रहा है
Basically, most of the reverb is gone. You actually capture the underlying patch. I mean, it's not perfect because some of them, we make some assumptions here, but you get the idea, right? Or there are other equivalent applications. Here's one where this is again a friend singing the 5 vowels. And now here, there's something called a constant Q representation. In a constant Q representation, the frequency axis is not linearly spaced, it's logarithmically spaced. So when you logarithmically space the frequency axis, then changing a pitch in a linear frequency axis, if I change my pitch, the distances between all of the harmonics increases. If I in a logarithmically spaced frequency representation, if I change my pitch, the entire pattern just moves up and down, right? And so this is him going I, right? That's just him. And it's his voice, so it's the same spectral structure at different pitches. And if you decompose it, you can see the basic spectral structure coming out to the left and the pitch track coming out at the bottom, right? And that's it. And here's one which is even more interesting, the smoke on the water. The specialty of this one is that it's played on a single instrument, on a single string. You just play different notes and mix them up. But so the spectrum at every position is exactly the same. The only thing that changed is the pitch. And so if you decompose it, there's the basic kernel spectrum to the left. And at the bottom, you can see the structure, right? You can see the whole thing. Not beautifully, right? So again, all of this is true. This was panel and some. You can see how it actually pulls out the basic note of this voice and the basic note of the tympanum and the pitch track for the tympanum and its last. So again, there's nothing particularly complex in any of all of these fancy things that you just see. The math is just semantically constrained with algebraic decomposition. This is a spectrogram, but it doesn't have to be just spectrograms. You can go beyond spectrograms. Here is a collection of faces, a photograph of many faces. And so this picture is composed of a single patch. And the single patch is an average face, right? Which has moved around and positioned itself in various places. So if I decompose this picture into the composition of a single patch, here's the patch that comes up. It looks like an outline of a face. And here is the set of weights. It's a two-dimensional space. And you can see highlight that it's at the location of every single face in the image, right? Or here's something more interesting. This thing has 3 characters. The same 3 guys, all the reds, the A's are in green, the R's are in blue, the L's are in red. And if you look, and now this goes beyond 2 dimensions. Now it's 3-dimensional. 2-dimensional space, and the 3rd dimension is color, right? But the same kind of decomposition ends up giving you these are the basic units: the green A, the red N, the blue R, and the locations in the original image where they happen. We're not doing anything fancy. This is complete. Just pass the data into the algorithm. Or more of the same, right? If you let things reflect and stuff like that. So you make it transform and again. Or in this case, this is a video. There's a rubber band and the USB dongle and a ball which is sort of going around in a circle. And so if you decompose the video, which is now a 4-dimensional object, 3 colors in the 4th time, then you end up with these as your bases: the ball, the rubber band, the dongle. And you also will find out that the ball is going around. So you get the idea. I'm just giving you, fancier and fancier applications of essentially the same basic tool, which is non-negative decomposition of data. And non-negativity was constraintly applied because it was physically and semantically. We didn't change very much from what we did when we were doing eigen decompositions. All that happened was that we added an extra constraint. And we know how to apply constraints. We saw this in class number 4. Right? And that suddenly gives you amazing things, right? So we'll see more of the same kind of stuff.
Some more about optimizations, but are there any other methods besides just standard gradient descent that work better because we know things
So
are
these
going
are
to
not gradient descent. So these are like
okay.
so that's how these are derived. The L2 one is gradient descent, the projected gradient descent. Yeah, here. I see.
And is there a reason you use expectation maximization?